Okay, we're going to go ahead and talk about how to define these different three-dimensional shapes. And this is where it gets a little bit fuzzy. And so, unfortunately, we've got to end with volume. We've got to talk about it a little bit. But it does fall a little bit outside of what we've been doing in the past, because a lot of what we're talking about with volume actually is going to go back to ideas of calculus. And so really doing some proofs and talking about three-dimensional space is kind of outside of the scope of this class, but you need to know the volume formulas, so unfortunately we're just going to have to deal with it. And this is kind of how your mathematics has been up until this point, is that you didn't really have the capacity to understand how to prove the Pythagorean theorem before you got to me, and so we really focused on that. So hopefully in the future you'll be able to derive some of these theorems a little bit more rigorously. But for now, let's just talk about the definitions. What do I mean when I say a prism? Well, all I mean is that I'm going to take a polygon, any polygon. Okay, so there's a polygon. It looks sort of like a trapezoid, but not necessarily. And this polygon is going to be translated through space. So I'm going to take that polygon and I'm going to move it somewhere else. The polygon is not going to change size when it's translated. It's just going to move in space. And so I end up with kind of another polygon that's congruent to the one I started with. Those don't look congruent, but forgive my terrible three-dimensional drawing. So I'm not going to change the size of my base, a little vocabulary, but I'm just going to translate this polygon through space, and what I end up with is something that looks like this. Right? So there we have our prism. So a prism is going to, really by definition, have to have bases that are congruent, because we're taking the same base and translating it through space, and then all of the space that's sort of contained when that polygon is translated is going to give us our prism. Now a cylinder is going to be the same way. We are going to go ahead and define a cylinder as having a circular base and not like a elliptic base or some sort of weird mix of curvy and straight. But of course we can have prisms with any type of base. But for cylinders, we're just going to talk, we've got a circular base, and now that circular base is going to be translated through space, and all that space that is being used up is going to become our cylinder. Now, a pyramid and a cone, there's a little bit of translation going on, but that's not all that's going on. What happens with a pyramid or a cone is we're going to start with a base. Again, we're starting with some sort of polygon for a pyramid, and we're going to translate, but at the same time we're going to dilate. Now, what does it mean to dilate? There's a very rigorous definition for dilation, and we just don't quite have time to get to it. So think about dilation as a transformation, so some way that I'm going to transform a figure or a polygon or a shape that's going to create a similar polygon or shape by some dilation factor. Okay, so not only am I going to be moving this quadrilateral, but it's also going to be shrinking into a point which we call the apex. So forgive my drawing for these two. I'm sort of terrible at them, but I will do my best. So we've got a pyramid. So we are starting with our base, and we are moving our base and dilating it. So what that's going to do is it's actually going to give us sort of, let's see if I'm a little bit off here, but that's okay. The idea is that if I cut a slice through the pyramid, what I would end up with is a polygon that is similar to the base, because that polygon is being dilated. So any cross section that I kind of slice open my pyramid, I will end up with a face that is similar to the base that I have, that I started with. Okay, so what are some other things we need to know? Okay, well, I guess I should say too that a cone is just going to be the same idea as a pyramid. We're going to go to an apex, and we're going to be translating the circle, also dilating the circle. So the circle will be getting smaller until it gets to a point. Okay, so a little bit more definition here, and kind of the pieces of the puzzle. Went too far. So here we have a prism and a cylinder. And you see we've got two bases. I've talked about the bases. That's going to be the polygon that gets translated. When the polygon gets translated, it's going to create faces. So you see this green shaded in piece. This is a face of this polyhedron. Okay, that's the name we give for a three-dimensional shape that has polygons as its sides. So you've got lateral faces, and that's just all the faces that are not the bases. Okay, so lateral face is a face that's not a base. You get a vertex whenever you have three different faces meeting at a point. You get an edge when you have two faces meeting at a line segment. You can see here that I've drawn a line from a point on one base perpendicular, or line segment, from a point on one base perpendicular to the other base. And this is going to represent the altitude or the height of my prism. And the same kind of thing is going on here. We only have an edge down here and one edge up here because this all the way around the cylinder, you know what cylinders look like, we won't have no edges. And so there's just that one lateral face that goes all the way around. And you still have your two bases. We also call this prism that I've drawn here, this is a right prism. And it's a right rectangle. Well, I guess I can't really tell if it's a rectangle. So a right quadrilateral prism. So you name prisms by their bases. And when I say that this is a right prism, all this means is that if I pick a point on the top base and I draw a perpendicular and I get a point on the bottom base, these points are in the exact same location on both bases. So this is what is called a right quadrilateral prism. Now, okay, you're telling me, well, doesn't that always happen? Well, this is called an oblique prism, and again, forgive my drawing. So an oblique prism, we're translating that polygon, but we're not going, quote unquote, straight up, right? We're sort of translating it at an angle. And so you see if I pick a point on the top base and I draw a perpendicular, well, that perpendicular doesn't hit the bottom, this base at all, right? Because this is such a tilted parallel or prism. Now these are very hard to draw, so if this makes no sense to you looking at my diagram, then go ahead and go online and look for an oblique prism and a right prism, and you'll sort of see what the differences are in those two. So this is an oblique prism. Okay, what about some pyramid vocabulary? So here in our pyramid, we have a right rectangular pyramid. You see that right down here. We have a base, just one this time. We have an apex, which is also a vertex. They're both... The apex is specific to pyramids and cones, and the apex is a type of vertex. So you're seeing that we also have lateral faces. We have 4 lateral faces, and they are triangular. And right now, we're looking at a right rectangular pyramid. So what does it mean to be a right pyramid in this context? What does it mean to be right? Well, if I draw a perpendicular from the apex down to the base, if it is a regular base, so I'm looking at a regular polygon, then that altitude should hit the circumcenter of my base. It's directly in the center of a regular polygon, right? It's the center of the circle that goes through all the vertices in the polygon, which you learned when we looked at the regular polygon and compared it to the circle. Now, if you have a rectangular pyramid, then a right rectangular pyramid is going to be one where the altitude hits, when I go straight down from the apex, that altitude is going to hit the intersection of the diagonals. So if this is a rectangular pyramid, right, then I'm going to hit the intersection of the diagonals right there. Now, if you have something other than a rectangular pyramid, or it's not regular, then really you're going to have to be given more information. If you think about a triangle, there is really no set center of a triangle, right? Maybe you're talking about the circumcenter. Maybe you're talking about where the angle bisectors intersect. Maybe you're talking about where the median, or, well, you don't know what a median is. We didn't quite get that far. But there's lots of different places that could be the center, maybe where all the altitudes intersect. And so to talk about the center, quote unquote, of a triangle doesn't quite make sense. So if you are given a right pyramid, and it's not a regular polygon as a base, and it's not a rectangle for a base, then you'll need a little bit more information to figure out what that regular, or what that right pyramid would look like. Now, yes, you can also have oblique pyramids. I didn't even try to draw one. And again, if you're looking at oblique pyramid, this is just going to depend on the problem you have as far as where your apex is going to be and how it's going to interact with the base when you drop a perpendicular. So really, that's kind of all we've got as far as definitions, and you can see all the definitions in your lesson 16, and check those out, and then we'll kind of keep going through the lesson, and we'll start thinking about how do we actually find the volumes of these shapes, and we'll also introduce a sphere.